Welcome to the fourth week. This is the first module, and at this point we are going to sort of shift gears and get into another level of complexity as we deal with more of oscillations. So, in the last 3 weeks we saw what we called simple oscillations of, let us say, a single particle. Then we added another realistic effect, which is to add damping to it. We saw what a damped oscillator is, and then we also added another realistic effect, which is to give it continuous supply of energy, so that it keeps oscillating. So, all this we did for a single particle, but if you think carefully about what you actually see around you, many of what you see as oscillations, you would see that very rarely you would come across oscillations of a single particle. Often what you see is a collection of particles working together, oscillating together. So, you, for example, I even just push the air here, okay, it is going to set off oscillations in some way, and the disturbance that I created just by pushing the air here moves forward. In fact, that is what happens when I speak or when anyone speaks. Okay. You are able to hear me speak simply because the sound waves, which are essentially disturbances, pressure variations in the medium of air, are created and they get propagated. So, here a lot of these molecules are coupled together, somehow they act together and help in propagating waveforms. So, let us today start with how we describe these coupled phenomena. In principle, we want to study what happens if I couple a large number of particles, maybe 10 power 23 atoms, Avogadro kind of number. It is going to be fairly complicated. So, let us begin by first starting to learn what happens if I couple just two of them. We had already seen everything about, or at least the basics of single particle oscillations, and now we are going to progress towards studying coupled oscillations, as you can see, of many particles coupled together, and this coupling can take very many forms. It could just be a string that is coupling two particles here, or it could be a spring, or maybe there is nothing physical like a spring or a string. It could just be the effect of the potentials, potential at each site, for instance. So, the coupling can take very many forms. It does not have to be always a spring or a string or something that is visible to us. So, keeping all these generalizations in mind, let us try and formulate and see whether we can solve coupled oscillations. And as we do that, it is a good idea to again look back at one system which is a sort of paradigm for oscillations, that is the simple pendulum. So, we have already done this in fair bit of detail in the very first week. What I have is a simple pendulum, and here I have the equations of motion written for this simple pendulum. We saw all these things, and once I have the equations written for it, I can immediately extract the angular frequency, and the angular frequency depends only on the acceleration due to gravity, which is g, and L, which is the length of the pendulum. And from this, it is straightforward for me to get what is time period, because I know that omega is 2 pi by time period. If I substitute, I will get the standard formula for the time period of a simple pendulum. Now, let us go one step further. So, as I said, we are going to couple two oscillators. Now, we can ask the question, what if I couple two pendula? So, here is what I plan to do. So, let us say that I have one pendulum here, another pendulum here, and I am going to couple these two pendulum through a spring, and we shall assume that capital L is the length of the string here and m is the mass of these bobs that you see here, and k is the spring constant for the spring. And as usual, we are going to make very idealistic assumptions which may not be true in practice, but nevertheless are useful to obtain some good understanding of ideal systems. So, what are the idealistic assumptions? So, we are going to assume that spring does not have a weight, strings also do not have weight, and the bob here is a point particle, and so on. These are the standard assumptions, and most importantly we will continue to stick to small angle approximation, in the sense that if you remember in the case of simple pendulum, the more correct equation of motion was theta double dot plus g by L sin theta is equal to 0, and we said that sin theta is approximately equal to theta if displacements are small, and this can be mathematically written as theta being much smaller than 1. So, we are going to stick to this so called small angle approximation even in the case of coupled pendulum. So, to begin with, we need to write the equations of motion. Let me first say that the left hand side pendulum as x pendulum, and let us say that I am displacing it by an amount x, and the pendulum on the right hand side I am displacing it by an amount y. So, I am going to make a general assumption that x is greater than y. So, let me first write the equation of motion for the x pendulum, m times x dot, and that would be equal to minus m g by L times x. This assumes that you have nothing else, in the sense that there is no y pendulum. If there was only x pendulum here, then this is the equation of motion, but we know that there is a y pendulum and there is a spring. So, somewhere they should make their appearance, and here it makes its appearance in this way. So, there is a second term which corresponds to the effect of having a spring coupling the two bobs. Let me explain to you how this term comes, but before I do that, let me also write the equation for the second bob corresponding to the y pendulum. M y double dot is equal to, now you notice that I had made this assumption that x is greater than y, in which case you can imagine that if your x bob, which is this one, is being pulled in this direction, and if x is the displacement of the x bob and y is the displacement of the y bob, the natural length of the spring has changed now. So, it is going to act against the acceleration of the x bob. So, the change in length is x minus y, and since it is acting against the acceleration of the x bob, you have this crucial minus sign here. On the other hand, under the same condition, it is going to help the acceleration or favor the acceleration of the y bob, which is why you have a plus sign here. And just to repeat, so the compression of the spring by my assumption is such that it is helping the y bob to accelerate, whereas it is acting against the acceleration of the x bob. So, if I had made this assumption as y greater than x, then these signs would sort of exchange with one another. Okay. So, with that in mind, we will now have to find a way of solving this equation. Now, of course, if k is equal to 0, it is like two independent pendula, and two independent pendula, we know the solution, we have studied that already. It is just that there are two independent pendula and they do not interact with one another. So, what the coupling does is to make them interact with one another, okay. They are no more independent. So, you disturb one, it is going to affect the other. To begin with, first let me rewrite these equations slightly differently. So, I will write it as x double dot is equal to minus g by L times x minus k by m times x minus y, and y double dot is equal to minus g by L times y plus k by m times x minus y. So, since each of them is a pendula, that is the main oscillating object, and we know that for a single pendulum this is my omega square. I am going to call the quantity g by L as omega 0 square, in some sense natural frequency of a simple single pendulum. So, with all this we can rewrite the equations as follows. Okay, so, I have just substituted omega 0 square for g by L. Now, the question is how do I solve it? It is still a second order ordinary differential equation like the one we had for the case of simple pendulum and many other systems. But the crucial difference because of coupling is the following. So, if you look at the first equation here, this one. So, it is an equation for x, displacement of the x pendulum, but you notice that the x pendulum has contribution from the y pendulum, that somehow appears in the equation. And similarly, you look at the equation for the y pendulum, it has contribution from the x pendulum. So, in that sense they are coupled. Earlier we could easily solve it because there were no such couplings. Now, you need to know y to be able to solve x, and to solve y you need to know x. So, it is a kind of chicken and egg problem. How do we solve it? So, let us see, let us try a few things. So, the first thing I am going to do is to add and subtract the equation, okay. You will see why I am trying to do that. So, let us call let us say that this is equation 1 and this is equation 2. So, let me first add the two equations. If I add the two equations, so I have an equation which looks like this. So, before we understand this, let me also do the second part that I said. So, now I have added equation 1 and 2. So, that is what I have done here, add 1 and 2, that is what gave you this. Now, let me subtract the 2. So, I want to do the following, subtract. So, I want to subtract 2 from 1. So, that would give me, now I have simplified and written this equation. So, I have the second equation which is resulting from subtracting equation 2 from equation 1. Now, if you look at the structure of these two equations, it will be clear what we will do next. In the first equation that I have here, the variable always comes as x plus y or x double dot plus y double dot, and in the equation here it always comes as x minus y or x double dot minus y double dot. So, which means that I can in fact invent a new variable which is, for example, could be x plus y, let me call it u. And if u is x plus y, u dot will be x dot plus y dot. Similarly, u double dot will be x double dot plus y double dot. And we can also, following the same recipe, you can also call v is equal to x minus y, and v double dot will be equal to x double dot minus y double dot. Now, it is clear what I need to do, simply substitute these things into these equations. Let me write that. So, if I take the first of this equation, so this one now would become u double dot plus omega 0 square equal to 0, whereas this equation here would become x double dot minus y double dot is v double dot. So, that would be v double dot plus omega 0 square, x minus y is v plus 2 k by m is also v, 2 k by m into v is equal to 0. Of course, this can be further simplified. So, v double dot plus omega 0 square plus 2 k by m into v is equal to 0. Now, examine these two equations. They look like equation of a one dimensional oscillator, and the frequency is omega 0 square in the first case in this one, and the square of frequency in this case is omega 0 square plus 2 k by m. Now, you see that the equation for u depends only on u, v does not enter the picture here, and similarly the equation for v depends only on v and it does not involve u. So, we seem to have magically uncoupled the two oscillators, and what was our formula for doing that? We simply went from one set of coordinate system to a different set of coordinate system. So, originally our coordinate system was defined by x and y, and we went from x and y to u comma v, and the transformation was u is equal to x plus y and v is equal to x minus y. And this appears like a very magical transformation, which transformed a coupled set of equations given by equations 1 and 2 to a uncoupled set of equations given by this equation 3 and 4. So, let us call it equation 3 and this is equation 4. In the new coordinate system that we wrote down, which is this x plus y and x minus y coordinate system, the equations of motion are here in front of you, and as I pointed out, you could see that each one is now an independent equation. It does not couple to the other. So, the equation for u does not involve v and the equation for v does not involve u. So, it has made our life easier because we know how to solve these equations. So, in the case of this equation, the frequencies are omega square is simply equal to omega 0 square, the quantity that sits here. And in the case of this equation, the frequencies are omega square is equal to omega 0 square plus 2 k by m. And you will notice again that as a cross check, you can set k equal to 0, meaning that spring constant is 0, there is no spring at all in the first place. In such case, you just get back two independent pendula, both of them have a frequency which is equal to omega 0. Okay. So, it is consistent to that extent. Let us set V equal to 0, in which case V being equal to x minus y, and that being equal to 0 would imply that x is equal to y. Okay. So, the constraint here is that x and y, the displacements of each of the pendula should be exactly equal and in phase. So, what we are looking at is that two pendula are essentially oscillating in phase like this, and the spring here does not play any role. So, it is like these two pendula which move like this in phase. So, the spring that is in between them is neither extended nor compressed. So, there is no effect of the spring at all in this particular mode of the coupled pendulum. So, this is the case where x and y are equal. So, x and y, just to indicate what they are. So, this is x and this is y, both the displacements are equal. So, that is the physical meaning of the first set of first equation. Now, the second equation, which is the equation for V, in which case u could be 0, which would mean that x plus y is equal to 0, which implies that x is equal to minus y. So, that would correspond to the pendulum having the following pattern of oscillation. So, you could see that the pendula basically move like this, it is what is called anti-phase. So, in the other case we saw that they were in phase, both of them move in this direction like this, and in this case they are in sort of anti-phase. So, in fact, this is called in phase motion, both the bobs are in phase, and this is called anti-phase motion, because as you can see, if when one of the bobs is trying to go in this direction, the other one actually goes in the opposite direction. So, there is a phase difference of pi between these two oscillators. In this kind of a motion, what happens is that the spring is always either compressed or it is extended. It never has its natural length. Unlike in the first case, in the case of in phase oscillation, the spring is never extended or compressed. So, the effect of spring is absent, which is why you see that the frequency is simply the frequency of the single pendula. Both the pendula, even though they are coupled by the spring, they do not feel the effect of the spring in the first place. On the other hand, in the antiphase mode, the spring is always either, like you can see the way I have drawn, it is either extended or compressed. So, the effect of spring is there, and which is why you have this k coming here. So, in this case the frequency depends on the spring constant k. So, these two patterns of oscillations, in phase and antiphase, they are often called modes of oscillation, and these two frequencies are called the normal mode frequencies, and these two patterns are called normal mode patterns, or simply normal modes or normal mode oscillations. To summarize this part, we started with trying to couple two pendula. We used a spring to couple the two pendula, as we have done here, and we wrote down this equation of motion, and we realized that the problem in solving this equation of motion was that the first of the equations, or the equation for x, involved the variable y, and the equation for y involved the variable x. So, it is coupled to one another, and what we did was to add and subtract the two equations, and we got two other equations, which is this equation 3 and 4, and magically it looks like they simply got uncoupled. In the new variables u and v, we have two equations of motion which do not interact with one another, which is very good for us because we know how to solve them, and straight away I could extract the frequencies without any further work. And we could also physically interpret these modes of oscillations. As I said, these patterns, the collective pattern of oscillation is called the normal mode. There are two normal modes, there are two particles, basically two bobs. So, there are two normal modes, and corresponding to each of the normal mode or each pattern of oscillation that it exhibits, you have two frequencies. The two pattern of oscillation is, one is where both of them are in phase like this, they oscillate like this, and the other one is where they oscillate like this, they maintain a phase difference of pi. In the modules ahead, we will see even more complicated versions of such coupled pendulum, until the point when we couple a large number of these.